In this video, we're going to be going over rotational motion equations and how they're similar to linear motion equations. So here we have our rotational motion kinematics cake equations, where we have constant acceleration, which is our condition for being able to use these equations. And basically, they're the same as the translation of motion equations, except you have variables that you just sub in for velocity, for your displacement, and for your acceleration. So those are these variables here. So let's start off with our first question to demonstrate how to use these. So a 15 centimeter diameter circular saw blade rotates at 1,200 RPM. Find the speed of the teeth. Convert RPM to rad per second first. Okay, so what we were given was the diameter, the radius. So we know that from this we can find the radius. From this, turn this down. So we know that the radius is just equal to half of that. So that's going to be 15 over 2, and that's going to be 7.5 centimeters. But we want it to be in meters because that's our SI unit. So that's going to be 0.075 meters. So that means that if we get the rotational speed, that's going to be our omega. So that's going to be equal to 1,200 revs per second. Now we have to convert RPM to rad per second. So now that's our omega, right? So we know that 1 revolution is equal to 2 pi radians. Like, think about it. Like, when you go in a circle, it's 2 pi radians. So that's 1 revolution. And we also know that 1 minute is equal to 60 seconds. So we can utilize these two conversion factors so that we can cancel things out and get what we want. So we get 2 pi rad divided by 1 revolution, which is the first ratio. And then we have 1 minute over 60 seconds. Now from here, we just have omega is equal to 40 pi rad per seconds because of the fact that we can see that we keep seconds. We can see that revs cancel out, and we can also see that our minute, we can see that cancels out. So now we just have this. Oh, this is revs per minute. This is why. This is actually minutes. So that cancels out. That's why that cancels out. Okay, so that's how we get that. But we want to find the speed of the teeth. So we can use the tangential speed formula. Tangential speed connects our translational and our rotational motion. So our tangential speed, that's going to be v is equal to omega r. So that's translational velocity is equal to the angular velocity times the radius. So that's going to be equal to our omega was our speed, our rotational speed, Our rotational speed is 40 pi, and then our radius is 0.075. So that's going to be, if you plug that in, that's 9.42 meters per second. Find the tangential velocity of a ball twirled on a 1.3 meter long stick if it makes 5 revolutions every second. So we're given the radius of 1.3. We're also given 5 revolutions. So 5 revs. And we're given t is equal to 2 seconds. So now what we can do is we convert revolutions to angular velocity. So we know that omega is going to be equal to 5 revs per second, because we know we know the unit for omega is going to be in revs in rad per second, right? So we have to get that into rads per second. So we know we have that in 5 revolutions. In order to do 5 revolutions, it takes 2 seconds, right? So that happened in 2 seconds. So just write S. We want to convert this into rad per second. So we can write our ratio earlier, 2 pi rad divided by 1 rev. That's going to equal to 5 pi rad per second, and that's our correct units. So we can see that over here, we saw that revs canceled out. So that's how we got our answer. So now we have to use the tangential speed formula, which is this. We use that up there. Velocity is equal to angular velocity times the radius. So your velocity is going to be equal to 5 pi times 1.3. And your velocity is going to equal to 20.4 meters per second. So that's going to be your answer. Find the velocity of the moon in miles per hour if it makes one revolution every 28 days and has an orbital radius around the Earth equal to 250,000 miles. So we have the radius here. We have the radius is this. And we also have the period. T is equal to the period, which is the time period that it happens, 28 days. So what we can do is we can convert our time. We want this in hours. So we're given 28 days, right? And we want this in hours. So how do you do that? Well, we know that 28 times 24 is equal to 672 hours. There's 24 hours in a day. Yeah. In one day. So yeah. Okay, so now we can find the circumference of the orbit. So we know that the circumference is going to be of a circle is equal to 2 pi times the radius. So we know that if we find this, we can plug in 2 pi, and our radius is 250,000. So we know that the circumference is 1.57 times 10 to the power 6 miles. Now, we need to find the linear speed. In order to do this, we know that velocity is equal to distance over the time. So we know that the distance that we traveled was 1.57 times 10 to the 6. That's because we were moving in a circular orbit. So, and our time was 672, which we found earlier. So that's just going to be 2.34 times 10 to the power of 3 miles per hour if you plug that into your calculator. And you can also write that as 2,300 miles per hour. Now, let's move on to our next question. A car starts from rest. Its wheels accelerate to an angular velocity of 20 radians per second after 5 revolutions. What is the wheel's angular acceleration? So we're given the initial angular velocity because it starts from rest, right? We know it starts from rest, so that means that angular velocity initial is equal to 0. And we also know it accelerates to an angular velocity of 20. So we know that the final is going to be equal to 20 radians per second. And we know that the angular displacement, which is equal to delta theta, that's going to be equal to 5.0 revs. And we can convert this. 5.0 revs, we know that that's going to be equal to 5.0 times 2 pi. So that's actually equal to 10 pi radians. Now, we have to use the right kinematics equation that uses all these things that we have. So what do we have? We have angular velocity, we have angular displacement, and what can we do? We need to find the angular acceleration. So if you're thinking about this kinematics equation, omega f squared is equal to omega initial squared plus 2 times the angular acceleration times the delta theta. Yes, this is the one. So we can substitute our values. We have 20 squared is equal to 0 plus 2 times the acceleration times 10 times pi. So that's going to be 400 is equal to 20 times pi times the acceleration. And then if we divide, we have that acceleration is going to be equal to 400 divided by 220 pi. We see that the 2's cancel and a 0 cancel. So we have, I'll just write that cleaner. So we have that this is equal to 20 over pi. And that's going to be equal to 6.4 radians per second squared. And this is the right units. These are the right units for acceleration. So that's how we know our answer is right. Okay. A top spins and slows down at an angular acceleration of negative 1.5 radians per second squared until it topples. It will topple at an angular speed of less than 24 rotations per second. The top toppled after spinning for 45 seconds. What well, what was the top's initial angular velocity? Okay, so we're given that the angular acceleration is equal to negative 1.5 radians per second squared. We're also given that the time that it's spun for is 45 seconds. So that's our time interval. And we also know that our final angular velocity, WF, is going to be equal to 24 revs per second, which was given over here, because we can convert that rotations per second to revs per second. So what can we do? Well, we can convert the final angular velocity into rads per second, which is what we have to do here. So WF is equal to 24 times 2 pi. That's going to be equal to 48 pi rads per second. Now we have to use the right kinematics equation. Again, what do we have? We have our angular velocity final, and we also have our angular acceleration, and we have our time. So the kinematics equation that we should choose is angular velocity final is equal to angular velocity initial plus our angular acceleration times time. So that's going to be 48 pi is equal to angular velocity initial plus negative 1.5 times 45. So this is going to be 48 pi is equal to angular velocity initial minus 67.5. Now, we need to solve for what do we need? We want the initial angular velocity. Let's solve for that. This is going to be equal to, adding 67.5, we have, so we have 48 pi plus 67.5. This 48 pi, that's going to be 150.8 plus 67.5, and this is going to be 218 rad per second. A bullet fired from a rifle initially rotates with an angular velocity of 2,200 rads per second. If the bullet is slowed by friction and it rotates 480 revolutions during its 1.4 seconds of flight, what is the angular acceleration of the bullet? So let's write all our given values. So we know that our initial angular velocity here is going to be equal to 2,200 rads per second. And we also know that our angular displacement is going to be equal to 480 revs. During a 1.4 seconds of flight. So that means that we know that our time interval is equal to 1.4 seconds. So now what do we have to do? Well, we need to get it in radians. So what do we have that's not in radians? This is not in radians. So this is going to be delta theta is equal to 480 times 2 pi. And that's going to equal to 960 pi radians. Now, which kinematics equation can we use that has all of these things? So we know we have angular velocity initial, we have change in angular displacement, and we also have a time interval. Okay, so then that means that we have to use delta theta is equal to omega initial t plus 1/2 times angular acceleration times t squared. So now we can substitute in our values, and we have 960 pi is equal to 2,200 times 1.4 plus 1/2 times the angular acceleration and 1.4 squared. So if you simplify that down, you have 960 pi is equal to 3,080 plus 0.98 angular acceleration. So we need to solve for angular acceleration. So our angular acceleration is going to be 960 pi minus 3,080 divided by 0.98 after doing some algebra. And then if you just solve this, just plug into your calculator, you get, this is approximately going to be negative 65 rad per second squared. that's going to be your angular acceleration. A bicyclist is coasting downhill and puts on the brakes. They have to stop in 1.5 seconds to avoid a stopped car. Their wheels are rotating at an angular velocity of 20 rads per second when they stop braking. What angle do the wheels rotate by the time it stops? What angle do the wheels rotate by the time it stops? So we were given that our initial angular velocity is 20 rads per second. We're also given our final angular velocity is going to be 0 because it stops. And we also are given that our time is 1.5 seconds. So we need to find angular acceleration. So we're gonna use WF is equal to W initial plus acceleration times time. 0 is equal to 20 plus our angular acceleration times 1.5. So angular acceleration is going to be equal to negative 13.3 rad per second squared. Now, we have our angular acceleration, but we need the angle that the wheel stops. So then we have to use a second kinematic equation, actually. So then we have that delta theta is equal to omega t plus 1/2 acceleration t squared. And this is going to be delta theta is equal to 20 times 1.5 plus 1/2 times negative 13.3 times 1.5 squared. So delta theta is going to equal to 30 minus 15, which is equal to 15 rad. That's going to be our angle. Now, how many revolutions is 15 rad? Well, we know that revolutions is going to equal to 15 over 2 pi. So that's going to be approximately 2.4 revolutions. A boat starts with its propeller at rest and reaches 20 radians per second. If it takes 50 revolutions to get up to this velocity, what is the angular acceleration of the propeller? Okay, so kind of have to write a little small, so I'm just going to zoom in. So we had that our initial angular velocity was 0, and our final was equal to 200 rad per second. And we knew that the angular displacement was 50 rev. So rev is not the unit you want, so you need to convert that. So that's going to be 50 times 2 pi is equal to 100 pi rad. So you can actually, or it's okay. Let's keep that there. So after this, we choose our equation that has all these 3 variables, which is going to be omega f squared is equal to omega initial squared plus 2 times angular acceleration times theta, change in theta. So that's going to be plugging in our values, 200 squared is equal to 2 angular acceleration times 100 pi. So that's going to be 40,000 is equal to 200 pi times angular acceleration. Angular acceleration is going to be 40,000 divided by 200 pi. That's going to be 200 over pi. And that's going to be 64 rad per second squared.